In the last video, we talked about what matrix transformations were. Really, we just take a vector b1 through b2 and we multiply it by a. That's going to be a transformation from Rn to Rm, or from the Euclidean space of dimension n to Euclidean space of dimension m. All right, the following theorem tells us that linear transformation between Euclidean spaces and matrix transformations are equivalent. So if I have a function, then T is a linear transformation if and only if there is an m by n matrix A, so that T is T of A. So T is just multiplying by that matrix A. All right, so we'll use the notation square bracket T for the matrix corresponding to a linear transformation T. Hence, T of V is you multiply V by the matrix A. All right, so let's prove this. We're going to start by proving that if I start with a matrix and I multiply vectors by it, I get a linear transformation. So we will show T of A is linear. All right, so let's do it all at once. So I'm going to look at T of A of V1 plus K V2. That means I'm going to multiply V1 plus K V2 by A. I can distribute. Oops. And then I can bring the K out. These are really properties of matrix multiplication. And so that is A of TV1 plus K, oh, sorry, no A anymore. Oh, I guess the A comes here. That's where I wanted to put it. All right, TA of V1 plus KTA of V2. So yes, TA is linear. All right, so we have a linear transformation. Whatever matrix you start with, you have a linear transformation. Now we're going to go the other way, and that one is more surprising. If you have a linear transformation, then there's going to be a matrix, and your linear transformation is just T of A. All right, in fact, that A is unique, and it's going to be that you apply T to the standard basis. So the first column is T of E1. Second column is T of E2, and so on until you get to T of En. All right, so I want to show that T of AV is going to be TA of V. All right, so I started with any linear transformation. I define a matrix that way using that linear transformation, and I want to show that T and TA are the same. So let me give V coordinates so that we can actually see what happens when we multiply them. All right, so let's look at TV. I could write V as A1, E1. Do you remember what E1 is? E1 is 1, 0, 0. E2 is 0, 1, 0. It's just a standard basis and so on. And so it's easy to come up with the coordinates when you have the standard basis. That's what we usually use when we write the coordinates here. All right, then I can split it. I'll get A1 T of E1 plus A2 T of E2 plus AN T of EN. All right, so two things I want you to notice here is we actually completely determine the value of T of any V by knowing the value of these elements. And that's why linear maps are simple. Let's check that that corresponds at TA of V. So I want a V. So that's going to be TE1, actually let me put TE2 as well. TEN times A1 AN. All right, so when I take this product, A1 is going to multiply with the first column. A2 is going to multiply the second column for every row, right? For the first row, for the second row, for the third row, and so on. And so what I'm going to get is A1 TE1 plus AN TEN. Sorry, I'm always low on space. I swear I actually write these out before I do the videos, but I always write bigger when I'm talking to you guys somehow. All right, plus AN TEN. All right, so these two are the same, and that's what we wanted to prove. So yes, T is T of A. All right, here's the takeaway from that theorem for a linear transformation T from Rn to Rm. If you want to know what the matrix associated to this linear transformation is, all you have to do is apply T to the standard basis, and those are going to be the column of your matrix. That's it.